Welcome to The Explainer. Today we're going to talk about something you probably do dozens of times a day without a second thought. Clicking save. It feels totally instant, like magic, right? But what's happening under the hood is, well, it's a masterpiece of engineering. So let's dive in.
Okay, picture this. You've just typed out a simple phrase, "Hello world," in a text editor. You move your mouse, you click that save icon, and boom, it's done. It feels instantaneous, but that one simple click actually kicks off this incredibly complex and honestly fascinating journey from your screen to its permanent home on your disk.
So before your data can go anywhere, the operating system has to do some prep work. It needs to create an official record for your file. You can think of it like the file's birth certificate, or maybe its passport. It's a blueprint that gives it an identity in the system.
See, every file is actually made of two key things. First, you've got the data itself. That's your hello world. But then there's the metadata. And this is all the information about the data. What's the file's name? How big is it? Who's allowed to open it? When was it made? It's basically the file's whole backstory.
Okay, so where does the computer keep all this info? Well, it uses a special data structure called an inode. And the library analogy here is just perfect. The inode is like the index card in an old library catalog. It tells you everything you need to know about the book, the author, the title, where to find it, but it's not the book itself. The actual story is somewhere else on the shelves.
Right, so the system has its little index card, the inode. But how does your program, your text editor, actually get permission to interact with that file? It can't just wander into the library and start writing in the books. It needs a library card.
And it turns out, pretty much every program on the planet, I don't care if it's written in Python, C++, or whatever, follows the exact same three-step dance. First, it has to politely ask the operating system to open the file. Once it has permission, it can read or write its data. And then, and this is super important, when it's done, it has to close the file.
Now, when your program opens that file, the OS doesn't give it back the file's long name. No way. That's inefficient. Instead, it hands over a super simple number, like a little ticket. We call this a file descriptor. It's just like the librarian handing you a slip of paper with a number on it. From now on, you don't need the book's title. You just use that number. It's fast and simple. And get this idea is so fundamental that every single program you launch automatically gets 3 of these tickets right off the bat. File descriptor 0 is for standard input, which is usually your keyboard. 1 is for standard output, your screen. And 2 is for standard error, which is where all the error messages go. It's the basic toolkit for talking to your computer.
Okay, but hold on a second. We're talking about hard drives here, right? For many of us, these are physical, mechanical things with spinning parts and moving arms. This whole process should feel slow. So, why is it almost always completely instant? What's the trick?
Well, the secret, and it's a really clever one, is something called the buffer cache. Instead of writing your data directly to that slow mechanical disk, the OS first dumps it into a temporary holding area in your computer's super-fast RAM. By the way, this is exactly why you can lose recent changes if the power suddenly cuts out. Your data was sitting in that buffer, waiting to be written permanently.
The logic here is actually super simple, and it boils down to this. Talking to a hard drive is slow because it involves physical movement. So it's way more efficient to gather up a big chunk of data in that fast buffer and then write it to the disk in one go, rather than making thousands of tiny separate trips.
You know how a YouTube video buffers? It loads a chunk of the video ahead of time so you get a smooth playback even if your internet is a little spotty. That's exactly what's happening here. The buffer cache smooths out that huge speed difference between your processor and the disk, making the whole experience feel totally seamless.
Okay, so our data is sitting pretty in that super fast buffer. Now for the grand finale, how does the system find a permanent spot for it on the actual disk? I mean, it can't just chuck it in there randomly.
Your hard disk isn't just a chaotic mess of data. No, it's organized with like military precision. It's broken down into these millions of tiny fixed-size chunks called blocks. The file system is the master map, the digital librarian that keeps track of every single block, which ones are empty and which ones belong to which file. And the super block, that's like the master blueprint for the whole operation.
Okay, we've looked at all the different parts of the puzzle. Let's put it all together and trace that journey one last time, from our hello world to its final destination.
So that one little click you made, it kicks off this amazing domino effect. The OS creates an inode to hold the metadata. It hands your app a file descriptor, a ticket. Your hello world text gets zipped over to the lightning-fast buffer cache in RAM.
And then finally, the file system looks at its map and writes the data from that buffer to its permanent home in some free blocks on the disk. All in a flash.
And what this all really shows us is the power of something called abstraction in computing. It's absolutely brilliant. Your text editor app doesn't need to know about disk blocks. The operating system doesn't care what you typed. Each layer does its job and completely hides the messy details from the layer above it. And the result is a simple, clean experience for you.
So the takeaway here is that this kind of invisible genius is everywhere. It's in every click, every tap, every command you issue. The real magic isn't just what we see on the screen, it's in all these elegant, hidden systems working together perfectly to make our digital lives possible. It really makes you wonder, doesn't it? What else are we taking for granted?